Hi, this is Shoven Shrivastava, and this presentation is for the final project that we have been doing for the time series course at Northwestern. And this project is to predict the total number of cases, uh, like for dengue fever, in certain Pacific area or and the Southeast the Asia region. So dengue fever is a mosquito-borne disease, and it is possible to predict the total number of cases based on the environmental data collected by the various user federal government agencies, and these agencies are Center for Disease Control and Prevention, and National Oceanic Atmospheric Administration, and U.S. Department of Commerce. So we have the data set where we have number of variables, and we'll use those number of variables to predict the total number of cases, so that government around the world can uh, can take some this preventive actions to deal with like this dengue fever. So in recent year, dengue fever has been spreading, and historically, the disease has been the most prevalent in the Southeast Asia, where the monsoon is very prevalent, like in summertime. And when monsoon arrives, like it brings a lot of diseases with itself. So we have so I started with the data exploration and the transformation, and I went through all the variables that we can use to predict the total number of cases. So, like some of the data is like station max temperature, station minimum temperature, station average temperature, station precipitation, which plays a major part in the spread of the dengue fever. And then we have data for and then we have a data for the forecast system reanalysis measurement. So so we have number of variables for that, like reanalysis of the satellite precipitation amount in millimeter, and so on. So what I did for EDA, that I first look for all the null values which is present in the data set, and then I used an LOCF function to impute those nulls or nans with the very from the nearby data points. So that's how I imputed the like nan values, and then I draw like some diagram to get some understanding about the data set. So these are the two diagrams which I built, which gives the pretty good idea about how the data set is. uh, and then I drew all like histogram for all the data points to see that how these variables are distributed, and if we need any transformation. So these are the diagram or like histograms, and then I looked for the correlation between the variables, that what are the best variables to build the model. And when I looked at all the correlation like variables, that how they are correlated and how they are correlated with the total number of cases, I came up with this like 7 data points, which uh, which I think is highly correlated with the total number of cases. And these are reanalysis, specific humidity, and dew point, and average temperature, and minimum temperature, and the reanalysis max air temperature and the min air temperature. So we'll start like building our model based on these 7 variables, or 6 variables. So since this is a count problem, then I started with like Poisson model, and then I built a like auto ARIMA model, because like mostly the data set is based on time series, because we have year and the year of the week, like week of the year. So I built ARIMA model, and then I built Poisson model, and then I built like zero inflated Poisson model, because there are a lot of zeros in the data set. So I thought that that may give us like more like definite predictive like value. And then at the end, I build a model of this negative binomial model. Uh, uh, and then at the end of it, just to check that just to check that like if I can fit a linear model, I build that one too. But the R square value is very low for the linear like multivariate regression model, so I completely disregard that. And and then I tested all the accuracy for all the model, and it seems that the Poisson model like has the best accuracy of 8. So the error is 18. So I think this is the most accurate like model like out of 5 model that I have built. And then yeah, and then I segregated the data set into San Juan, like both the cities, into separate data set, and then I built the model, and then I merged it back to see how it that how uh, and ran against that test data set. So accuracy of this, so I calculated the error rate. Poisson model has 18.34. Negative binomial model has 18.34, which is not very far away. They both are almost same. The zero inflated Poisson model is 23.3. I thought that this would be lower than Poisson model, but it came out more. And then multivariate regression model is like for that low square is very low. This is the formulation. So I divided the data set into training and the test data set, and then I built the model and ran the model against the like against the test data set, and then I ran it against the final test data set, which is being like which has been provided by like drivendata.org. So these are the some of the limitations that I thought that that is present, that I did not do much study into like variance inflation factor, because I think some of the like variables, independent variables, are highly correlated. So I can work on that in the future. So in conclusion, I that that working with the real climate data and its lesson to reduce the life-threatening pandemic is very good and very good learning experience. It can help saving the human lives, especially in the developing world where this is a real problem. Um, the humidity and the average temperature predictors showed significant for both the models. One of the key learning to implement is to implement this non-parametric. Uh, More advanced data imputation for null values could have been used, which I'll do it in the future. Thanks.